about astronomical techniques in X-ray and gamma ray. But before going into the techniques, I thought you may like to know what X-ray astronomy is about and what kind of studies one does in X-ray astronomy, and that will give you a perspective of what kind of instrument and what are the challenges in those instruments to be able to study objects in the way that we do. And what's known in the field today, and that tells you what more we want to know, and that would guide you in deciding what kind of instrument might be needed. So I would give you some basics of X-ray source characteristics, the objects and the science that we learn from them, and then would try to define maybe together with you an X-ray telescope or X-ray observatory, and then see what details we want to know to be able to if not make, at least design, if not design, at least write down the specifications for such a telescope. So X-ray astronomy is by and large study of extremes of the universe. X-ray astronomy allows you to inspect extreme densities, extreme temperatures, very high velocities, relativistic objects, enormous magnetic fields and strong gravity. Okay. And these things appear near black holes, neutron stars, or an exploding supernova, or where there you have relativistic jets and so on. The objects themselves are called things like active galactic nuclei. So throughout this talk I would be referring to many things that Professor Rajaram Nityananda mentioned in two of his talks on the first day, both objects and processes. So objects like active galactic nuclei, where you have a supermassive black hole at the center of a galaxy and which emits over wide energy band, but our interest is in X-rays. Then similar thing happens at a lower mass scale in stellar mass black holes. There are pulsars, magnetars, supernova remnants, transient objects or transients phenomena in the sky called gamma ray bursts. Then clusters of galaxies allow you to see baryonic matter in X-rays which is not otherwise observable. And by X-ray one means roughly the energy band of 0.1 to 100 kilo electron volt. Between 100 kilo electron volt and 1 million electron volt is somewhat like hard X-ray astronomy or gamma ray astronomy, and above 1 MeV is gamma ray astronomy. Many of these phenomena also produce radio. Okay. Many of these processes, for example, especially active galactic nuclei, magnetars, supernova remnants, etc., are also of very high interest in the area of radio astronomy. So you may have heard about or you will hear about them in the context of radio astronomy as well. Some of the key questions in high energy astrophysics. If you ask different people to list key questions, they will probably list different things, but these will probably appear in everybody's list. Okay. And many of us work in areas which somehow connect to these. One is formation and evolution of supermassive black holes. Okay. There are black holes known in very early in the universe. Okay. When the redshift was about, objects from which we receive light today are at a redshift of 10 or so, and at that redshift very massive black holes were formed with mass like 10 billion solar masses. So one important question in astrophysics is formation and evolution of supermassive black holes, and since black holes often show up in the X-ray band, they are of interest to us. Astrophysical jets, what causes jets to be formed and accelerated, because in jets you have extremely relativistic particles. There is a class of sources called ultra luminous X-ray sources. Again, you heard about Eddington luminosity on the first day. There are objects in the universe which in nearby galaxies we see them in detail, which emit or exceed Eddington luminosity by factor of as much as 100. So what allows them to do that? There are magnetars with magnetic field in the neutron star of about 10 to the power 15 Gauss. Okay. So formation of neutron stars with this kind of magnetic field, their evolution, their magnetic field structure, etc., are very open questions in magnetars. These are the objects where, or these are the phenomena where there are more open questions than answers today. Okay. These are very active fields of research. Properties of matter in extreme densities, like neutron stars have supernuclear density. acceleration of matter to very, very high energies is an important long standing question in astrophysics. You have cosmic rays accelerated up to an energy of 10 to the power 21 arcs. Okay. So, what causes that kind of acceleration? X-ray astronomy will probably allow one to probe one part of baryonic matter in the universe. Baryonic matter constitutes a very small fraction of total mass density of the universe, only about 4%. Even within that 4%, only a tiny fraction is observable to us because they emit in various wavelength bands that we study them in. One large fraction of this baryonic mass is still unobserved. Okay, and X-ray astronomy may provide a way of investigating them or establishing their presence. That is called warm hot intergalactic matter. I will try to go there quickly and then go on to X-ray astronomy. Supermassive black holes. Okay, at the center of our galaxy, it has been possible to image orbits of several stars, very bright stars, but in the infrared band. It has been possible to image take real images of these objects, the orbits, and that all of them indicate that they are all rotating around a central mass of about 4 billion solar masses. Okay, and that's a very strong evidence of presence of compact massive object at the center, and only astrophysical object that can possibly explain this is a supermassive black hole. A similar supermassive black hole in another galaxy has in fact been imaged, the region around the black hole. There is indeed a dark spot at the center, surrounding them there is a radio emitting ring. Now, not all of these objects are active at all times, but most of them become active at some or other times, okay, called active galactic nuclei. Yeah. Active is when such a black hole accretes matter from a companion, okay, and this matter, when it goes close to any infalling matter, when it falls close to a compact object like a black hole or a neutron star, in this case supermassive black hole, the objects can get heated. Many powerful astrophysical processes can start taking place there. They can become extremely powerful emitter, okay, not from the black hole itself, but from outside event horizon. Okay, they can also produce extremely powerful jets. So, when an object is active in this fashion, it is called an active galactic nuclei. Okay. So, astrophysical jet, this one is a sketch, but that one is a real object, a real image. You can see black holes often produce and accelerate jets, extremely relativistic and extremely collimated jet. Okay. So, what produces and what causes acceleration of material in the jet is a very an important topic in astrophysics. Ultraluminous X-ray sources, while many galaxies have a massive black hole at the center, which is the AGN, outside it can still have very, very bright objects, and these objects cannot be explained by ordinary black hole. Typical black holes have mass in the range of, say, stellar mass black holes mass in the range of about 10 solar masses. Okay, a 10 solar mass object has to exceed its luminosity, Eddington luminosity by factor of many, to become as luminous as these objects. Okay, this is a very active area of research in astrophysics. You have magnetars, where a neutron star with extremely high magnetic field is rotating, it is slowing down, but unlike radio pulsars, slowdown of this magnetar itself is not sufficient to power the X-ray emission that we see from them. Okay. Neither that can create occasional huge bursts from these sources, and this is explained if they have extremely high magnetic field, but it is a very active topic of research. These magnetars actually connect to many other astrophysical phenomena that we see today. Cosmic rays, I am sorry, the energy scale is not seen here. This is in electron volt. So, cosmic rays, you can see the enormous energy range that is covered, okay, going from about an MeV to 10 to the power 21 eV. Okay. Cosmic rays are seen, and they are accelerated up to extremely high energies. One knows that in some places or in certain objects in the universe, like supernova remnants, when there is expanding material, there are shocks, and around shocks you can have particles accelerated. But that does not explain acceleration of particles up to these high energies, 10 to the power 21. Okay. 10 to the power 21 arg is more than probably the energy that tennis ball carries when it is subbed. Okay. That much energy that much energy carried by a single nuclei. Okay. So, what causes in astrophysics acceleration of particles to such high energies is a very important question. Another thing I said, this is baryons in the universe. Baryons, I mean observable matter itself constitutes a very small fraction, only about 4% of total energy density of the universe. Among that also a large fraction of this is not observable, at least not observable in the optical. For example, in clusters of galaxies, the picture on the right, the extreme right, the blue objects, yellow blue objects, those are galaxies. Okay. So, you have clusters of galaxies, they emit optically, but if you add up all of their masses, that turns out to be a small fraction of total mass. Okay. You look at the same object in X-rays, okay, individual galaxies may not be observable because these are distant objects, but intermediate in between the galaxies is actually filled with a very thin, only about 10 to the power 4 atoms per cc, 10 to the power minus 4 atoms per cc, but this gas is hot. Okay. And these objects are so large that the total amount of Bremsstrahlung emission, or if the column density is high, you can as well see them as a black body emission. All of these can emit copious amount of X-rays, okay, and that is how you see this large fraction of baryonic matter in the universe, but still that does not account for the total baryon mass in the universe. So, large scale simulations of the universe, if you start with the perturbations one sees in the cosmic microwave background, if you extrapolate from there, okay, if you start with that kind of density perturbations, and if you do simulations, you find that there will be filaments but in between them, in the filaments, there is probably a large amount of baryonic mass lying, but until today this has not really been observed directly. Okay. X-rays may provide, but that day is yet to come. Okay. So, these are the objects where you have various interesting objects and astrophysical phenomena which produce X-rays, and we study them. So, let me take you through few interesting kinds of observations in astronomy, in X-ray astronomy. I will give you few examples of each kind. Okay. One kind of astronomy is by doing timing, it is called photometry. Okay. You just measure in small intervals of times the number of photons coming from a source, okay, or for each photon that you record from a source you note down the time, that is called photometry. So, in X-ray timing I will show you some examples of what kind of science is done, what kind of measurements are done. You have a neutron star which is accreting material, and this material forms a disk, and this material in the disk is going around the neutron star. Now, very close to the neutron star, if you calculate the Keplerian angular velocity, okay, because the neutron star has a mass of about 1.4 solar mass, but a radius of only about 10 kilometers. So, at that radius the Keplerian angular velocity is hundreds of hertz. Okay. So, if in the material if you have some sort of inhomogeneity, that can produce a oscillation in the amount of X-rays that you see. The neutron star itself can be rotating with angular speed as much as several hundred times per second. Okay. If the neutron star has a small magnetic field, the material that is falling onto the neutron star, the radiation can have small anisotropy, okay, and that anisotropy will show up as a pulse signal. Okay. But to detect that, you need to detect sufficient number of X-rays in a very short interval of time. Okay. You need very, very large detector. Yeah. Neutron stars are not entirely neutral. At the center they are mostly neutrons, but as you go towards the surface it is not entirely neutron. Okay. There are iron atoms and electrons. The crust is mostly formed of iron. Neutron stars have magnetic field, and a low magnetic field neutron star can rotate very fast, okay, and you can have a pulse signal from them, but to detect this pulse signal you need very, very large detectors because they are spinning very fast, and if you need to detect sufficient number of photons at different phase intervals of this rotation, you need very large detector, you need to record those photons with sufficiently high accuracy. Once you have that, you can have signals like this, the one shown here, this is at 400 hertz, close to 400 hertz from a neutron star. You just take the light curve, which is the intensity distribution as a function of time, take a Fourier transform with this, and you will have this signal. This neutron star is a binary system because it is accreting material from a companion. If your detector is large enough that in a short interval of time you not only detect a pulse, you can determine the arrival time of the pulse with very high accuracy. Okay. Neutron star is going around the companion in an orbit. When the neutron star is close to you, the pulse emitted at that time will reach earlier than when the neutron star is farther away from you. Okay. So, if you are able to time these pulses very accurately, you will see a small modulation in that. Okay. And if the detector is large enough, again you can derive this kind of pulse arrival time delay. Okay. And if you do that accurately again and again and again for either this kind of pulsar or some other kind of pulsar in a binary, you will be able to determine that the orbit themselves, okay, may not be fixed, the orbit itself may have an evolution. Okay. So, if you subtract a linear term of the orbital ephemeris, you may end up with a measurement of evolution of an orbit. Okay. So, this is an example of doing X-ray timing with very high count rate and very high precision, and that is another example of doing this X-ray timing over a long interval of time, okay, which allows you to measure something a very slow process, for example, orbit of an X-ray binary system. Okay. These are all some extreme examples of timing studies with X-rays. On a neutron star, occasionally the yellow curve in the bottom, that is the X-ray intensity profile of a neutron star. Okay. Material falling onto a neutron star, occasionally it can flare up, because the infalling material is some sort of a fuel, it is a composition of hydrogen, helium or pure helium, okay, and this can have thermonuclear fusion. Okay, sorry, thermonuclear burst source need not be a pulsar, okay, can also be a pulsar. So, the yellow one is the X-ray intensity profile of such a source, there is material falling, there is X-ray produced, and occasionally this infalling material suddenly can catch a fire. They go through thermonuclear flash, the X-ray intensity can suddenly increase by factor of 10 or so, and then the material cools down. In few tens of seconds it can cool down. During this process, at very short intervals of times, you can see additional pulsation, because this fire may not be on the entire surface, it may be localized on the surface of the neutron star. Okay, that would give you some sort of a a rotating hotspot and therefore a pulsation. Now, to be able to measure that in a very short interval of time, you need extremely large area detector, and you need to record the times of photons with very high accuracy. It is not very difficult kind of instrumentation, but that is what you need to be able to do X-ray timing with high precision. These are X-ray timing at very fast time scales. Now, X-ray objects are of many different kinds in the sky. Their timing characteristics are vastly different. Okay. Here it is X-ray light curve of a very well known black hole source. Okay. A black hole has what? You may have heard about the black hole no hair theorem. A black hole has mass, it has angular momentum. Okay. Black hole is an entire black hole is defined by that. Now, if you have infalling material, the infalling material will have some mass infall rate, and it will start with some infalling angular momentum. So, you are starting with very few numbers, but this infalling material then develops some characteristics in a black hole, and the same black hole can show many different kinds of light curves. Interestingly, you may find it difficult to believe that it even switches between one pattern to another pattern in a very systematic manner. Okay. I would not get into lot of much details about that. If anybody is interested, you can pick up these papers and read or discuss with me. So, the same source can show many different characteristics, and it requires you to investigate or observe these sources with high timing accuracy with a large area detector for long time. There are several hundred bright X-ray objects in the universe, in our galaxy and nearby galaxies and further away galaxies. Many X-ray sources, or a large fraction of these X-ray sources, are actually highly variable, because they are powered by accretion. The accretion itself is not a stable phenomena. Okay. They are powered by accretion, and there are other related processes. The main thing is that most of these X-ray sources are highly variable, not only at short time scales, at long time scales as well. Okay. Here I have how many light curves of 18 such sources over several tens of years. Okay. You may think about, and they can show very characteristic, each one of them has different long term intensity profile, and that tells us a lot about these sources. But you may question yourself, what kind of observatory will allow you to measure long term light curve for tens of years, okay, of a large number of sources in the sky. Okay. Just think about it, what kind of X-ray astronomy first of all has to be done from space. There are many sources in the sky. Okay. And is it possible, or how is it possible to have long term light curve of 10-20 years of all of these bright sources in the sky? Okay. We will come back to this when we discuss instrumentation. X-ray timing is not an isolated thing, you not only do it with your instrument, okay, you often need to connect it with what has been measured with other instruments, okay, and often that connection brings in interesting things. One perhaps the most remarkable example I will show you is that of connection of X-ray astronomy with gravitational wave. Okay. Again Professor Rajaram on the first day showed you when the first gravitational wave was detected, that was from a black hole merger. Later on neutron star merger was seen, okay, that is called double neutron star merger, and this is the signal of the double neutron star merger. As the merging took place, the frequency went up, okay. This is the gravitational wave signal as a function of time, okay. Simultaneously with that, with an X-ray detector, okay, an X-ray flare was seen. Gravitational wave allows you, detection of gravitational wave allows you to identify from roughly from which part of the sky the signal has come. Within that part of the sky, there was an X-ray flare, okay. Later on it was demonstrated that X-ray flare actually was because two neutron star merger also caused an explosion of energy output, and that explosion is seen in the form of a gamma ray flare, that is a gamma ray burst. Okay. The interesting thing here is that the gamma ray burst was detected 1.7 seconds after the gravitational wave. Okay. Okay. So, gravitational wave merging happened, within 1.7 seconds there was an X-ray flare or gamma ray flare that has been detected. Now, imagine if this flare was detected few seconds earlier, or if this flare was detected 10 or 20 or 100 seconds later, okay, much of astrophysics, much of gravitation or lot of things related to this would have to be rewritten. The simultaneity or looking at X-ray data along with some other observatories is as important as that. Okay. We saw a gravitational wave merger, immediately following after that there is a gamma ray burst. If this gamma ray burst was earlier than this, earlier than the gravitational wave, or if it was much later, a lot of astrophysics would have to be rewritten. Okay. So, this therefore was very satisfying. That would be the details of the process, as soon as the merging happens. After that, how the material of the remaining material, it formed a black hole, the remaining material, how that assembled and what led to the flares, etc. So, there is a lot of detail to learn from that as well, 1.7 second delay. But this at least tells us, and this object was probably at a distance of 40 megaparsec, so 120,000 light years away, it was very far away. It tells us that the gravitational wave and light travel time, okay, both traveled at the same speed. That was the take home point here. Okay. X-ray spectroscopy, some examples. When you have this accretion onto a compact star, okay, you produce X-rays from the accretion disk, from a surrounding corona and so on. This radiation reaches us, but this radiation not only reaches us, it shines everything surrounding it, right, even the accretion disk. And that can produce K fluorescence emission, iron fluorescence emission. Okay. What is fluorescence emission? In iron atoms, if you hit it with a photon of energy higher than the binding energy of the K shell electron, one K shell electron can be knocked out, that is the photoelectron emission. Then an L shell electron can fill up this. Okay. The balance of that energy, difference between those energy can be emitted as an X-ray, and that has an energy of 6.4 kilo electron volt. So, in the X-ray spectrum, after subtracting the continuum, emission, we are left with this kind of an iron line. You can clearly see there is an iron line at 6.4 kV, okay, but a good part of this also has a low energy tail. That is explained if this radiation is coming from very close to a black hole. The radiation which is coming out is actually suffering a gravitational redshift. It has to overcome the pull of the compact star, producing this low energy line. Okay. So, this is called, this is one of the most remarkable spectroscopic result in X-ray astronomy. You will see more with the most recent instrument in X-ray spectroscopy, which is on board this observatory called CRISM. This is the spectrum of one such X-ray binaries. The iron line here, now this instrument has such high energy resolution that you start breaking down the iron line into multiple components. Okay, you have iron K alpha line, and in this part if you zoom in, you can see a 6.4 kilo electron volt iron line, which is from near neutral iron. But here very strong radiation from the compact star actually has caused ionization of all material surrounding it. Ionization to such a degree that iron has how many electrons? 26, right. Most of the electrons have been taken away from the iron atoms. You are left with some electrons with one single some iron atoms with iron nuclei with one single electron, so it is a hydrogen like atom, or some with only 2 electrons, it is a helium like atom. Okay. So, spectroscopically you can identify the hydrogen and helium atoms, helium atoms and neutral atoms, okay, with such angular resolution. And not only that, within the helium like atoms itself there are intercombination lines and forbidden lines and so on, and one is able to distinguish all of them. This allows very detailed, I mean this level of spectroscopy allows you to study things that I do not have time to get into, but this is the what to say state of the art in X-ray spectroscopy today. Sometimes you may want to do timing and spectroscopy together. Okay, that is not so difficult, because in X-ray astronomy every photon that you are recording its time as well. So, whenever you do spectroscopy you also have the possibility of doing time resolved spectroscopy, that is spectroscopy of the same object at different times. Why would you do that? One example is here. I need to finish this part in 5 minutes. You have an X-ray binary, there is a compact star, a black hole or a neutron star going around the companion. Now, if the observer happens to be near the orbital plane, then every orbit will have an eclipse, right. If you compare the X-ray spectrum during eclipse and out of eclipse, this is the spectrum out of eclipse when the emission is dominated by what is coming from the compact star. During eclipse, that compact star is behind the companion, okay. Most of the emission that is emitted from the central star is blocked, okay. All that you are seeing is the emission which is emitted from here, but then reprocessed from the material surrounding it, okay. It is only the reprocessed emission which has a path to reach us. That then shows up in these emission lines in 6.4 kV band, because this is reprocessed emission. Sorry? No, these companion stars are optical stars, their temperature is of the order of let us say 10,000 degree, okay. They are not X-ray bright, they are not X-ray bright to this extent. So, whatever you are seeing is reprocessed emission from the surrounding material. There are other signatures that this is indeed reprocessed emission, but in this talk I would not have time to get into those. Yeah. This is the emission line, this is 6.4 kiloelectron emission line. So, when X-ray is getting reprocessed from the wind, it can get reprocessed in 2 ways. One is from the electrons, it can get scattered, Thomson scattering, or it can produce a fluorescence emission. Okay, the fluorescence emission will dominate in such cases, and that is why these are of interest. Another kind of time resolved spectroscopy is for a pulsar. For example, you can do what is called phase resolved spectroscopy. Okay. So, if you look at a pulsar, it has a cyclotron line, this again Professor Rajan mentioned on the first day, pulsars can have cyclotron line because radiation is coming through very strong magnetic field. Sometimes you may want to see the cyclotron line at different pulse phases. Okay. Here is one example where a neutron star, the X-ray spectrum from it at different pulse phases is showing different cyclotron line energy, and it is only detected a small fraction of its total pulse phase. Okay, let us say the total spectrum is divided into 30, total pulse phase is divided into 30 smaller phases, of which in only about 5 of them the cyclotron line is seen, it is not seen in other cases. This could be explained if the neutron star has this kind of an accretion stream, and the radiation which is produced here is passing through this accretion stream to reach us, and that will produce a cyclotron absorption. But this will only be seen in certain pulse phases when this, as this whole system is rotating, only when this accretion stream is along our line of sight will be seen. So, to study this, and this is only one example, there are many such examples or different kinds of examples where you need to do timing and spectroscopy simultaneously, okay, or you do spectroscopy at different time intervals or different phase intervals. You may want to do imaging and spectroscopy together. Okay. One example is you look at a supernova remnant, the radiation that is coming out from a supernova remnant. Okay. It can have two kinds of emission. One is the outflowing material, when it is interacting with the interstellar material, there are shocks formed. That shock causes acceleration of particles. Those accelerated particles can cause synchrotron emission. But the outflowing material also has various elements, because we know that anything other than helium in the universe was produced inside the stars. Okay, they are produced inside the stars, but how do they come out to form second population of stars, third population of stars, and the planets, etc. Everything that we are formed of has been produced inside a star and has come out. Okay. They can come out only during the supernova explosions. Okay. So, supernova explosion.
Like this elemental analysis of spectroscopy, you can do that even in the visible spectrum. Is there anything extra we get by doing spectroscopy?
Not everything may emit optical. You have to have suitable condition for emission of optical light. These are the objects where you have condition for emission of X-rays. A supernova remnant like this is not optically as bright, or neither would have the optical emission lines for the study. Optical emission line or more than emission line, absorption lines are produced when you have a background source. Okay. So, here what happens is, for example, in this supernova various elements are synthesized, but when it is the supernova has exploded, okay, it looks like this material that has been thrown out is not isotropic. Okay. So, you make the spectrum of this, and then you make images in different narrow energy bands corresponding to various elements, and you can find that how elements have been produced and thrown out during a supernova explosion. Yeah.
So elements like metals are actually more seen in X-ray.
Yes, because their K alpha emission, their X-ray emissions, I mean their inner shell transactions are all fall in the X-ray band.
So if you have to see what are the elemental composition of some star,
No, elemental composition of a star is used by the absorption lines in the star, so which is the photospheric radiation which is coming out, it is coming through some material which then produces absorption lines. Okay. X-ray line is produced when you shine something with X-ray emission which is higher than the binding energy of those corresponding atoms, and then it produces fluorescence line. Fluorescence line will allow you to study ionization states, okay, and of course the abundances. Okay, I want to go through these parts quickly. Similarly, one does X-ray polarimetry, and one would also want to do timing and polarimetry. For example, if you are looking at a pulsar, you want to do polarimetry at different pulse phases. If you are looking at a supernova remnant, you may want to do the polarimetry in different locations of the supernova remnant, because particle acceleration, interaction of material with magnetic field might be different in different locations around a supernova remnant. So, let me not go into much more details of this. We get to the instrumentation part. Okay. One thing about X-ray astronomy is, or all of astronomy, if you consider, astronomy covers more than 10 to the power more than 20 decades, of which a very tiny band, more than 20 decades in either wavelength or energy. Okay. A very tiny band is the optical band. Okay. In the optical band all radiation reaches us, and again in the radio band the sky is transparent. In the infrared band, different locations at different frequency ranges, it is semi-transparent. For everything else, you have to go to space. Okay. You have to send your observatory to space, except extremely high energy photons like 10 to the power 15 eV or so. They can cause secondary particles in the atmosphere, and those can be studied by eventually what light comes down or what particles come down to the ground. Okay. All other astronomy actually needs to be done from space. Okay. So, astronomy in the last 40-50 years has seen explosion in all other bands. Even in optical, you want to go to space because then you overcome the atmospheric seeing conditions. You got many examples of how X-ray astronomy is done in timing, in spectroscopy, and so on and so forth. So, now let us think about, if you were to talk about making an X-ray telescope, can we discuss what all we need to consider? Okay. I would like the next part to be little participatory. Okay. Let us think of, we are going to make an X-ray telescope. Okay. Making is probably too much, let us design an X-ray telescope. Okay. Or even design, of course, is not possible in such a short time. Can we think about the specifications of a telescope? Okay. Or even whatever is possible in a few minutes. Can you think about what are the things for which you have to think about the specifications? Okay. Can all of you contribute to this discussion? Let us say we are going to make an X-ray telescope or X-ray observatory. What would you like to be considered for this? Electronic signal processing unit. Okay. So, fine, electronics, that is an integral part of it, but with the electronics what would you like to do?
Firstly, what part of X-ray is observable from the ground?
Okay, so are you referring to the energy band? No, we have to go to space. Okay, for an X-ray telescope, let us consider we have to go to space. Okay, so are you referring to the energy band that we will cover? Okay, so one input I have got energy band. Volunteers, yeah. And what equipment will be required, we will discuss later. Okay, what will you do with this lens? What is the purpose of asking for the lens? So you need to bring the X-rays to a focus. Shall we call that? Give a name. Huh? Optics. So shall we? The criteria for the instrument, shall we call it angular resolution? You guys are experienced. Let let newcomers respond. So energy angular resolution. What more? Noise. So in the X-ray band, one thing is that we detect all individual photons separately. Okay. So in the detection of a photon itself, two kinds of noise may come. Okay. One is you are trying to measure the energy, but you may not be able to measure the energy accurately. That is one kind of noise. Another kind of noise is, so okay, we will have to get a technical term for that. The other thing is, when you are looking at a source, you not only detect photons from that source. Okay, if you may detect some extra photons from the nearby sky region. You may detect some unavoidable signal from the detector itself, because it is in space, there are charged particles going through, it may have some residual radioactivity, the electronic noise may produce some unwanted pulses and so on. So two kinds of noises. Okay. The second one, let us call it as background. Okay. Uncertainty in the background is a noise. If you know your background very accurately, any measurement you have, you can just subtract the background. It is uncertainty in the background, because any background level that you have, in every tiny measurement you would not exactly measure it, you will measure something more or something less. That unknown factor is called the noise in the background. Okay. And that is an important thing in X-ray astronomy. If you are detecting a signal from a faint source and your instrument itself produces lot of unwanted signal, that is a noise. Okay. So background noise, you want to minimize this. Okay, that is one. Other thing noise is, yeah.
Reducing calculation.
Let us write down that point. Other point is, you said noise, which is when you measure energy of a photon, okay, you may not be measuring it very accurately. Okay. That is another noise. Shall we give it a name? It relates to energy resolution or spectral resolution. Okay. You want to measure that 6.4 kilo electron volt line. I showed you two examples. With the most modern X-ray detector, you are able to measure the energy very, very accurately. That is why you detect those narrow lines. Okay. With an older generation instrument, you will see the line to be slightly broader. Okay. That is the instrument resolution, and that is that also comes from some sort of noise. So then the noise issue, one is background, other one is it leads to or it connects to spectral resolution. We often call it energy resolution. You were saying something?
Like we need to know what is the exact time that this X-ray has been
Okay.
generated at the star.
Generated at the star is a different question. At what time it is detected on the detector, let us think of that.
Good clock for that.
So shall we call that timing accuracy?
And we need to reduce relativistic errors if there are any like gravity.
That would not be done by the detector. Okay, that would not be done by the detector. That would be in your analysis, okay, or what you understand about the object. Okay, detector will not do any such thing. Detector can detect a photon. It can, or your desire is that you will record the time with very high accuracy. So there are two things. One is with what resolution you record the time. Okay, typically a microsecond is a good enough resolution for most detectors. But sometimes there are difficulties achieving microseconds, so you compromise and make milliseconds or things like that. For example, if you are reading out a CCD has a finite readout time, okay. So or finite exposure time. So photon falling within that exposure you can't resolve. Okay. So timing resolution has a limit, and accuracy of with what accuracy you record that time. For example, you might want to have a GPS on your satellite and record every event with respect to the time on the GPS. Okay. So you can get high enough accuracy, you can get certain time resolution related to your instrument. Okay. So, we got quite a few things: timing, accuracy, energy resolution, background noise, angular resolution, energy range. What else?
Do we have to account for the X-ray diffraction or something which might happen there? The diffraction effects.
How it may affect your instrument?
There can be like you can't get like you can't resolve it to a point. There will be a point spread function.
So, diffraction may appear in two different ways. If you are making an interferometric instrument, it may come into. Another is you can make use of diffraction. Okay, you can use gratings, right? Gratings are used, and you use diffraction to disperse the light based on their wavelength or energy. Okay, and then where a photon is detected tells its energy. Okay, so that somehow gets included in this point of energy resolution. Okay, you can make use of diffraction for getting high energy resolution. Anything else comes to mind? Yeah. Yes, you can make your detector with many different kinds of instruments, but how will that change the character of your instrument? So that character you have to discuss now. Yes, if you use a CCD which is made of silicon, let us say, okay, we will see little later. Silicon will absorb only low energy excess up to about 10 kilo electron volt. Beyond that, it will not have enough common time efficiency. If you use cadmium telluride, those are higher Z elements, so that will detect photons of higher energy, but low energy it may not give enough angular resolution, or it may not cross the threshold and so on. So energy range is decided by which instrument you consider, but energy range you have already included as a parameter. Cosmic ray induces background in the detector, so reduction of background is already included in our discussion. How about size of the detector? Size of the instrument. Okay, if you are looking at a non-focusing instrument, you just look at one source, through some pipe or something, restricting your field of view, then size decides how many photons you detect. Or if it is a telescope, then size of the telescope decides how many photons you detect. Even though telescope brings photons to a small area, size of the instrument, I will come to that. Let us just write down each point. So, no, resolution is a different thing. This is size. I know where you are coming from. If it is an optical telescope, then the size decides roughly what angular resolution you have. Not so in X-ray, because X-ray interferometry has not been used yet. Okay, so in X-ray it is size decides basically effective area. Okay, so in astronomy we call this effective area. Your instrument size may be anything. Okay, that multiplied by the quantum efficiency, or if it is a telescope, that multiplied by the telescope's let's say reflectivity. Okay, so effective area is as a function of energy. What is your photon collection area? Okay, it would be a fraction of the total geometric size of the instrument. So effective area. Please think. No, cooling system is not a specification for the telescope characteristic. Cooling systems, if required, you will have to do cooling, but that is not telescope specification. So cooling will be required if you are using, for example, CCD detector, it has to be cooled, or certain kind of semiconductor detectors have to be cooled. In some other areas, in infrared telescope, even the telescope itself has to be cooled, because otherwise thermal emission from that will ruin your measurement. Length of the telescope, why do you want to care about length of the telescope? Yeah, so that factor has already gone into angular resolution. If you are doing X-ray focusing, then for higher angular resolution or actually for higher energy also, you need longer focal length. So that factor has gone into angular resolution. Sorry? Good, very good. That is the technical term for that is field of view. If you have a telescope, what part of the sky at a time it can cover, that is called field of view. Now field of view has two aspects. One is, if you want to just study one source at a time, okay, then field of view does not matter so much. Okay, like a Cygnus X1 or some other pulsar or any other star, which is essentially a point object for us in the sky. If you want to study a point object, then field of view does not matter. But if you want to study multiple objects in one shot, okay, in one exposure you want to study multiple objects, then field of view is important. Or if you want to do imaging like a galaxy you want to image in X-rays, then field of view must cover that galaxy. Or if you want to study cluster of galaxy which can have angular size of as much as a degree, okay, then you need large field of view. So,
Imaging like is used for detecting transients
also. Okay, transient beings in another important thing about telescope. You mentioned FOV and you mentioned transient. Does that lead to something else?
how long exposure? How long
Okay, I will come to that later. Field of view and transient might tell you that you may have heard about gamma ray bursts. Gamma ray bursts can happen anytime, anywhere in the sky. Okay. So, you may want to look at the entire sky simultaneously at all times. Okay. That is one point. Another point is, if you remember, I showed you light curves of at least 18 sources, and there are actually 400-500 such sources. There are light curves measured for these sources, that is the intensity profile as a function of time. Okay. For last 30 years or so, we have continuous light curves of several hundred sources in the sky. Okay. What kind of instrument can give that? So, a telescope which looks at a tiny part of the sky cannot definitely produce, sorry, no, a telescope has a limited field of view, right. A telescope will have a limited field of view, it will only allow you part of the sky at a time. Okay. If you are interested in making an all sky map, you can use the same telescope, point in different directions of the sky, and after 2 years you will make an all sky map. Okay. Actually there are dedicated instruments for that. Okay. So, those are survey telescopes which you want as much field of view as possible, but a single exposure will only still give, let us say, fraction of a square degree or few square degrees and so on. That data you will have to stack, or no, not stack, you can make that kind of measurement continuously over different in different directions of the sky and eventually come up with a survey. So, you have to consider whether your instrument is a survey instrument or any instrument with a narrow field of view can be used for survey, maybe a limited survey and so on. So, you will have to consider that whether it is a survey instrument or not. A survey instrument may not be particularly good for single point observation. Okay. However, that also will not give you the long term light curve that I showed you. Long term light curves require what is called all sky monitors. Okay. You are coming to scanning. So, one way of achieving all sky monitoring is you have something which looks at maybe not a narrow part of the sky, but at least a strip. There are ways of making strip detectors which at a time monitors one strip, then you rotate the whole thing in sky and thereby cover all sky monitoring. So, all sky monitoring is one way or the necessary way for getting those long term or studying the long term variations of X-ray stars, and X-ray stars are so variable. Okay. Unless you know their long term properties, you actually do not know much about them. So, we will call it that all sky monitors. All sky monitors can be of two types. One is one that actually looks at the entire sky at a time. Of course, if it is near Earth, then Earth will block some part of it. Okay. But if it is far away from Earth, then Earth may not block much of the sky, and you can actually look at the entire sky at a time. But if you look at the entire sky, you may not have enough angular resolution. So, there are compromises to be made, but that is exactly the kind of detector you need to detect gamma ray burst. When a gamma ray burst appears in the sky, it is very sudden, rapid, extremely bright phenomena, okay, and you will detect it even if you are looking at the all sky and you have a very large background. So, all sky monitor comes in two ways, one is omnidirectional, another is scanning. Okay, you can have a strip and you spin the system, you can have.
So, I'd like to ask, how is it exactly different from an X-ray telescope? It's still a telescope with a different function.
A telescope which requires very detailed optics and so on is not simply feasible to make an all sky monitor omnidirectional instrument with a telescope, they are just not possible. So, omnidirectional instruments are slightly different kind, where one possibility is you can just have an open detector, as you are saying, you can have an open detector, you can have multiple open detectors, each one of them looking at a large part of the sky. Okay. Then a single photon you can't determine its position from one detector. Okay. You will have to take the ratio of counts in different detectors, and even that will not give high enough angular accuracy, but that is the best that can be done. Wide field of view, some sort of wide field of view instrument, if you rotate, you can do scanning and you can get all sky, you can investigate the all sky variabilities. When I talk about detectors, I will come to some more of this. Any other point? Okay, somebody had mentioned something like how long you can make an observation and so on. What is, so one way of looking at that is duty cycle, let us say. If you have an instrument, what is its duty cycle? Typically, if it is a low Earth orbit satellite, your source can get blocked by Earth, okay, in different parts of the orbit. So your duty cycle will partly get controlled by the visibility of the source, simply because Earth comes into field of view. Another thing is in around Earth there is a region called South Atlantic Anomaly region, or if your satellite is polar, then near the polar region the charge particle density is very high. Usually X-ray detectors, when charge particle density is very high, it is designed to reduce most of the charge particle induced signals, but a large fraction of it cannot be reduced, okay, or whatever is residual background is detected ruins your measurements. So charge particle regions are usually avoided for measurement purpose. So all of these things will decide your duty cycle. So duty cycle is another factor. Anything else comes to mind? I will move to the next part then. Okay. In about, you were saying something?
Like how much time it takes to observe patch of sky perfectly?
There is no perfect observation, you will always have desire for little more. Okay. So we will call that signal to noise ratio. This is somehow related to many of the things that we discussed before. It is related to background. If background is high, signal to noise ratio will be low. If you are trying to do spectroscopy, if your angular resolution is, sorry, if your energy resolution is poor, that will decide your signal to noise ratio. If you are doing certain kind of timing study, you know, there are effects that I will talk about called dead time effect, pile up effect, etc. So all of that affects signal to noise ratio. So many of the things that I said before will be related to signal to noise ratio. Those will go into deciding what is your signal to noise ratio, especially effective area, angular resolution and so on, energy resolution. Okay. So we came up with a huge list that we have to keep in mind if we are talking about an X-ray telescope, fine. So this is a list you guys came up in about 5 minutes after about half an hour exposure of 2x astronomy. So that's actually not very different from my list, which I have come up with after 30 years of doing X astronomy. Okay. So you guys have done a very good job. What I had in mind is effective area, energy range, angular resolution. Angular resolution, whether it is same across the entire field of view or not, is an important factor. Timing resolution has two more issues. One is dead time. Often your electronics will be such that when you detect a signal, the electronics is processing this signal, another signal it cannot process. That is one kind of dead time. Okay. So that also decides what maximum rate you can see. If it is a very bright object, you might get limited by dead time, or something called pile up. When one signal is, before one signal is read out, if another signal has fallen onto the detector, for example, that happens in case of CCDs. In a pixel, you give certain exposure, within that exposure if 2 photons are detected, CCD can't distinguish, and actually optical CCDs work like that only. The brightness at a point is decided by the total charge deposited. You can't calculate back how many photons may have caused that signal. Same in X astronomy. In X astronomy, one difference is that every photon you desire to record its time, record its location, that is imaging, and record its energy. Okay. But if 2 photons get merged, then the energy measurement is ruined. Okay. That is pile up effect. Spectral resolution we discussed. Polarization sensitivity, if it is a polarization instrument, then you have to define its polarization sensitivity. Background variability. Okay. Background is important, background variability is just as important or even more. Field of view, whether it is all sky monitor or not, omnidirectional scanning. Observational efficiency, uninterrupted observation, okay, is one aspect. Many of the X-ray sources have certain characteristics which you can establish only if you have a long uninterrupted observation. Now, with low Earth satellites, usually that is not possible, because of which there have been some cases like the current 2 big observatories, Chandra and XMM Newton, and prior to that ExoSat. These are observatories which are in a large elliptical orbit, and as you know, in elliptical orbit, when the source is farthest away, it has very small velocity. Okay. It actually spends more time when it is farther away than when it is near Earth. So they give very long uninterrupted observation of, typically compared to what you need for binary sources. Okay. So uninterrupted observation is one criteria for many X-ray telescopes. Another is response time for target of opportunity. Okay. This nowadays is valid for optical telescopes or radio telescopes as well, because one is studying many transient objects, gamma ray burst, well, let me not get into details. There are many kinds of transient sources where once the transient phenomenon is detected, you want to immediately as quickly possible observe them using in other wavelength device. For example, gravitational wave, if it is a double neutron star merger, we immediately want to see whether we detect a transient or not, and in across all wavelength bands. Okay. So, how quickly your telescope can respond to a requirement of a transient is also an important criteria for an X-ray telescope. Okay.
I have a doubt, like when you are observing such bursts, if it is a CCD kind of thing, you may not know that when this actual sudden spike came across.
Okay. In X-ray CCDs, the exposure is or the dead time is not that long, okay, but we will come to that. If you have a specific question, I will come to that. While thinking about X-ray gamma ray detectors, this is the most important diagram, which is how X-ray or gamma ray interact with matter. The X-ray has to first come and interact with detector material, right. This is the most important factor, where the energy is shown in the x axis, the material in which you want to detect the X-ray is shown in y axis. Okay. These lines show where the two processes are of equal likelihood. Okay. And on this side photoelectric effect is dominant, here to here Compton interaction is dominant, beyond that pair production is dominant. So, roughly up to about between let us say fraction of an MeV to about 5 MeV, Compton interaction is the most dominant process. Beyond and at a lower energy, photoelectric process is the most dominant. So, most of the X-ray energy band we detect X-ray photons by the photoelectric process with material which may be silicon, which may be cadmium telluride and so on. Okay. So, photoelectric process is most dominant in the low energy band, Compton is the lower gamma ray band, and pair production is the process for higher energy band. So, if you are detecting a 50 MeV photon, okay, 50 MeV photon is going to interact with matter only by pair production. Okay, you need a pair production telescope, nothing else will work. And if you are detecting an 1 MeV or 2 MeV photon, it is essentially Compton interaction. Your telescope is to be Compton interaction telescope. I will come to. I have exceeded my time. Sorry? Z of the observing material. Sorry? Is the atomic number, not redshift. Okay. Okay. So, X-ray timing, the most important thing is you need a large area detector, okay, and each photon timing has to be recorded correctly. That is mostly an electronic, electronics what does that, not so much about the detector. And when you are using large area detectors, you have to consider how to minimize the background. Large area means its internal background itself will be high, how to minimize that background. So, proportional counters, scintillators, these are basically materials for making very large area detector. Two issues one have to be careful about is dead time and pileup. Okay. Spectroscopy, there are many ways. One is scintillators. You can allow, and this usually works above about 20 kilo electron volt. The X-ray gamma ray photon is made to fall on a scintillating material where it is absorbed and causes ionization, and then there will be optical emission, and that optical emission is detected with the photomultiplier tube. So, every X-ray photon, and these days there are other devices as well, semiconductor detectors. So, every X-ray gamma ray photon will produce one pulse, and that amplitude of pulse is roughly linear to the energy of the incident photon, but photomultipliers do not give very good angular resolution. So, there is larger uncertainty in this. So, that is scintillator detectors. Proportional counters, if any one of you have experience of working with Geiger-Müller counter, okay, which are readily available off the shelf. Proportional counters also more or less work in the same principle. You the incident X-ray is absorbed in a gaseous medium. The energy which is deposited, part of it will be taken out by the K, the photoelectron. The medium will get ionized. The electrons will be moving towards a central anode wire, which is kept at a high voltage, and near there multiplication will take place because these electrons will keep colliding with the rest of the gaseous atoms, and finally a pulse, negative pulse will be produced on the anode. Okay. That pulse is a roughly proportional to the energy of the incident X-rays. So, this is good timing device and gives coarse spectroscopy as well. Yeah.
We use this thing for SEM and scanning tumbling microscope and
Okay. Proportional counters.
yeah, we shoot a X-ray photon to the material, like few of it observed and re-emitted.
Re-emission, fluorescence. Okay. So, many of the X-ray detectors, that is one issue which you need to keep in mind is the entire energy may not get absorbed in the detector, because most of these X-ray photons are getting absorbed by what is called photoelectron photoelectric process. So, a K shell electron is, and K shell has the largest photoelectric cross section. So, most likely it will be knocking out in K shell electron. Then there will be a fluorescence emission. That fluorescence emission may or may not get absorbed in the detector. So, for an energy incident energy E minus the fluorescence energy is what is deposited in the detector. So, sometimes you will have a response of this detector could be where the X energy is, and another response at E minus the fluorescence energy. Okay. So, they have complicated energy response, one needs to keep that in mind. There are other forms of gaseous detectors, I will not go into much detail. CCDs or semiconductor detectors are good spectroscopic devices, relatively easy to operate, where the material causes ionization. They have low ionization energy, so many ionization pairs are produced, and those are then captured. There is no multiplication in this kind of detectors. They give good energy resolution because large amount of initial pairs are produced, and they can have very small pixel size. So, therefore, one can do imaging with them, and these typically have to be operated at lower temperature. Okay. So, if you have a CCD or a semiconductor detector in space, you have to make arrangements for cooling it. There is additional burden of that. Most high tech detector in X-ray astronomy is for angular energy resolution, good energy resolution, is this thing called microcalorimeter, where you have the X-ray photon absorbed in a tiny piece of metal. Okay. That the few keV energy deposition onto that metal causes a small rise in temperature. Okay. That heat is then transferred to a semiconductor device which is kept at an extremely low temperature, few millikelvin, about 25 millikelvin. Okay. Now, imagine keeping a tiny device in space at very low temperature and maintaining that low temperature. Okay. That is a very challenging task, but has been achieved. So, the energy deposited by a single X-ray photon causes a small increase in temperature, which causes a change in resistance because it is kept at a critical temperature, and that resistance can be measured accurately, change in resistance, okay, thereby giving very accurate value of the energy measurement. These are the very high resolution energy devices. Then grating or Bragg reflection etc. are also used. Bragg reflection is a possible way, but has limited sensitivity. Coming to X-ray imaging, okay, there are multiple techniques. Most simple is collimator. It is not really an imaging. If you want to study one bright object in the sky and there are no other nearby sources in that region, okay, you can just have a detector and put a pipe in front or multiple small pipes in front. That just limits your field of view, okay, and you will be detecting most of the photons from the central source, or most of the detected photons will be from the central source. That is called collimator. A lot of X-ray astronomy has been done with simple detector and simple collimators. Astrosat has one of such things. You can have a pinhole or slit camera, okay, where you have a small pinhole and a position sensitive detector below that, you get an inverted image of the sky. Okay. There is actually currently such instrument working on International Space Station, and we ourselves use data from that. A better version of that kind of thing is called modulation collimator. You can have coded mask imaging. Astrosat has one such instrument. Coded mask imaging is you have a position sensitive detector. At some height above this, you put a coded mask, okay, alternate blocks of, or with a certain pattern, blocks of open boxes, okay, open squares and squares which are masked by some high atomic mass material, so that it blocks the X-rays. Now, if you have one bright source in the sky, okay, you will get a shadow of this mask. Okay, it is easy to convert and get the intensity and spectrum and position of that object. If you have multiple objects in the sky, on the detector you will detect sums of multiple such images, each one shifted, and then you get the sum of all of that. There are ways of converting this and still finding out positions of the, if there are bright objects in the sky and if they are sufficiently separated in angular position, then there are ways of inverting this and getting an image and spectrum of the sky. That is called coded mask imaging. But most advanced telescopes are the use grazing incidence optics. X-rays cannot get in an optical telescope or a radio telescope. What you have is you have a surface, the photons fall in, they get reflected. X-rays will not get reflected from a surface, X-rays will simply get absorbed. Okay. So, to have X-ray reflection, what you do is you take a surface, allow X-rays to fall at a small angle onto it. Okay. If it is roughly about less than 2 degrees incident angle, and if the surface is made of some high atomic mass material like gold or platinum and so on, then the light can get reflected. This surface, if you can make very precisely, this is a sketch of Chandra X-ray telescope, where you have is each one of those rings you can imagine is a bucket. Okay, the surface is slightly tapered, so X-ray photons falling onto it is falling at a small angle. The first part of the bucket is a parabolic, has a parabolic inner surface. So, photons get reflected once, the next one has an hyperbolic surface, it gets reflected once more and then they come to the focus of the hyperbola. Okay. This is a very precise way of doing X-ray spectroscopy. Remember, this is not interferometry, this is just ray tracing leads to this. If you are able to do this very accurately in Chandra telescope, that has been achieved, okay, and there are 4 such rings. Okay. So, it is just, you imagine a bucket, rainwater falling onto it, only the water that falls and hits the inner surface of it are then getting reflected and getting collected, and there are 4 such sets of buckets in Chandra.
We are following this method so that if we directly expose to the high energy X-rays,
They will get absorbed, they will get absorbed. It is only at small angle incidence photon can get reflected and thereby focused. Okay. So, this is called grazing incident optics. You have grazing incidence of X-rays onto a surface, but that only works up to about 10 kilo electron volt or so. If you want reflectivity at higher energy, then you have to have multiple such surfaces, which is achieved by putting alternate layers of high Z material, low Z material, high Z material, low Z material, and also use the spacing between them is changed to have response over a wide energy band. Okay. That is called grazing incidence optics from graded layer. This is this works in hard X-ray band only. This is one of the most challenging things to make in X-ray astronomy. Grazing incidence optics. There is some activity at, going on at RRI also towards that. X-ray polarimetry is done by the following method. Below 3 keV you can have Bragg reflection and then you can rotate the crystal. Okay. Between 2 and 8 kilo electron volt, the incident X-ray will get absorbed in the material and produce a photoelectron. The photoelectron will tend to go along the electric field vector. Okay. So, if your incident X-rays are polarized, the initial photoelectron track will be along the electric field vector, and if your instrument is such that that track can be imaged, then this photoelectron will cause ionization in the gas and that track can be imaged, okay, then you can do polarization with it. Another way of doing that is Thomson scattering or Compton scattering, where the incident X-ray you scatter it from a low atomic mass material, so that photoelectric effect does not dominate. If you have a beryllium or lithium block, then the X-rays can get, instead of photoelectric absorption, can get scattered. The scattering will tend to go more in a direction, so that the electric field vector does not have to change direction. Okay. So, scattering is mostly in the direction perpendicular to the electric field vector of the incident photons. So, such an instrument, if you rotate, you will see a modulation in the count rate, and that can be used for measuring X-ray polarization. If you have noticed, I have been talking about X-ray only. Okay, let me at least give you some glimpse of how imaging, spectroscopy, timing, etc. is done in a higher energy band. As you go to higher and higher energy band, it becomes more and more challenging. Probably most difficult area of astronomy to do any sort of imaging is in the Compton energy band, around few MeV, let us say 500 keV to tens of MeV. That is the most difficult band in astronomy, simply because the physics principle does not allow you to do direct imaging. Okay. First of all, no matter will absorb these X-rays, so you can't have shielding. Your detector has to be more or less open to entire sky. Okay. So, you will be detecting signals from almost entire sky, or at least 2 pi in the front hemisphere. All X-ray sources will contribute to your instrument. In such a case, how can you do astronomy? How can you do imaging? Compton detectors are such that you can have one set of detectors at the top, another set of detectors at the bottom. Okay. Now, if an X-ray gamma ray photon has come and interacted with the top, one of the top material, top detector elements, and got scattered, and after scattering it got detected in another detector in the bottom. Okay. So, now imagine you have 2 interaction events, one here, one here. You know that Compton interaction causes loss of energy. Okay. Now, if you are talking about a 1 MeV gamma ray, after an interaction by few degrees, after scattering by few degrees, you would have deposited or lost few keV energy in this detector. Okay, and then the scattered photon you detect with another detector, which is called a calorimeter. Okay, in the second detector as well, you measure the position. So, in both the detectors, you have measurement of position and their location. Okay, so the location allows you to draw a line, which is a one axis. Okay, and the 2 energies here and here tells you by what angle the photon has got scattered during the first Compton scattering. Okay, so this tells us that this photon must have come from somewhere in this ring. Okay, thereby it had around this axis, the line made by connecting these 2 points. If we calculate that the scattering angle was theta, then the photon must have come from one such ring. The ring also will have certain uncertainty, fuzziness about it, because these energy measurements are not very accurate. Okay, more accurate your measurement is, narrow is you are drawing the line either with a fine pen or with a thick pen, depending on what your angular energy resolutions are and position resolutions are. Okay. But for multiple such events, pair of events, you can draw many such circles in the sky, and once those circles start intersecting, okay, you will know that the points where maximum number of circles intersect are the regions of bright sources. The photons must have come from those regions. So, Compton telescope is a very challenging thing with limited sensitivity, but at the same time very interesting to do. So, with such Compton telescopes, what kind of things have been done? They can have decent energy resolution. Here is a map of the all sky map at 1.8 MeV. Okay, 1.8 MeV is the line, emission line of a radioactive species of aluminum that can only produced in, and that can come out in supernova explosion. Okay. So, this is one of the most direct examples that the metals are, high Z metals are in fact formed in supernova remnant, and these things must have happened within recent past. These are not historical. Okay. Otherwise, all of that would have decayed. That is one. In certain processes also produce positons, and electrons and positons can annihilate, producing 511 kV line. So, that kind of gamma ray telescope also allows you to make 511 kV map in the sky, and that is the spectral signature of that line, and this is the image. Okay. These are 2 examples. Last slide is on if you go to even higher energy, let us say few tens of MeV onwards, then the incident photons will cause pair production. Pair production is the only mechanism. So, pair production telescope could be like this. You have these alternate layers of some high Z material which are called conversion foils. If a gamma ray has come, it might interact with one of these, okay, and an electron positron pair is created. The electron positron pair will carry most of the energy of this incident gamma ray, and they will then produce track. Okay. And you have detectors in between which can measure the direction of those tracks. At each detector location, if you line them up, you will know which direction the electron tracks have flown and where was the interaction point. From there you can determine what is the direction of the incident gamma ray. Higher the energy, lower is the cross section, but your better is the measurement accuracy to determine the direction. So, this is one of the hardest areas of X-ray gamma ray astronomy.
So, you are measuring the position of electrons and positons, but it will change the momentum, right?
Here the energies are so much that most of their energy loss eventually happens in the calorimeters, not during these tracks. Of course, while doing this calculation, you keep track of, given this mass of material, what is the energy loss rate. A charged particle going through a medium basically loses energy by ionization. One knows those rates. Okay. So, from detection of these tracks and the final energy at these 2 locations, one will be able to determine the direction from which the gamma ray has come. Okay.
But as we are like quantum particles, there will be demolition measurements, right?
What is that?
Like the measurement itself will change the quantity we are
No. Here you are talking about extremely high energies, and your measurement uncertainties are as it is, your measurement uncertainty of energy are much higher than those parameters. Okay.
Sir, I think we are focusing on the position.
2 things. One is position, where the which allows you to positions at each of these locations, which allows you to measure the track.
Yeah,
Okay.
measure
And the final these 2 energies.
and time interval will find the
No, the light travel time within this is very small. So, one probably does not worry much about, unless there is an event going from bottom, you will detect that, of course. Okay. Whatever is coming from top, one can measure the track and measure the both energy and the direction of the gamma ray. So, that is that about various areas of X-ray and gamma ray astronomy, how these things are done. There have been 40 odd space missions, and for very ultra high energy gamma rays, what can be done from ground also, there are several dozen observatories. These have been established over last 30, 40, 50 years, and so the subject has evolved based on success of one instrument, what you have learned, that decides you how do you proceed with the next instrument, and so on and so forth. It has been a very long journey and there is a lot lies ahead. Thanks, then I will stop here. We have a tea break, right? If there is anything else to discuss, we can discuss outside.